Let us start lecture 40 and we talk about stress corrosion cracking, and mainly we will concentrate on mechanisms of stress corrosion cracking. In the way we will talk about hydrogen embrittlement or hydrogen assisted cracking, and later on we will touch upon corrosion fatigue, and then finally we will talk about protection routes or mitigation routes if some material is experiencing SCC or stress corrosion cracking or corrosion fatigue or hydrogen embrittlement. The course is corrosion failures and analysis. This is lecture 40. Topic is corrosion cracking or environmental assisted cracking or stress assisted corrosion cracking, and we are talking about mechanism of SCC or stress corrosion cracking. Now, we talked about two major mechanisms. One is dissolution based, where initiation plus propagation are dissolution guided. And stress, what does stress do? Stress opens up crack and allows corrosive to enter the crack tip. Now, there is other mechanism which is cleavage mechanism, where initiation is dissolution guided and growth or propagation of crack are stress assisted. Now, here also corrosion can play a role, but that is a second fiddle to the propagation of crack, but the stress is the main reason for the propagation of crack. So, there are several other mechanisms within those major mechanisms. One is dissolution based. If we try to find out what are the several mechanisms that are there in under dissolution based, if we try to find out, then first thing that comes pre-existing. This is one of the oldest proposed mechanism for SCC, pre-existing active path mechanism. And second is one can have film rupture model. Third is slip step model, and fourth one can talk about corrosion tunnel model. And interestingly, if we talk about, on the other hand, if we talk about cleavage mechanism, there are several other variations and out of that there are two segments. One is, you can say, one part is hydrogen assisted cracking, and the other one is, other variations are like film induced cleavage, then adsorption induced decohesion model, then one can think of Tarnish rupture model, then atomic surface mobility plasticity, surface mobility mechanism, okay, where we do not involve hydrogen. Okay. Like there is one more mechanism in this particular section, what is called I think this is fine. So, there are other subdivision of those models, but we can only discuss these 4 major variations. Then we can, in case of hydrogen assisted cracking, so there hydrogen is not involved, no hydrogen, but in this case we have hydrogen involvement. Now, one is definitely within this there are variations, like one is decohesion model, second is hydrogen embrittlement, one can also think of hydrogen induced local plasticity, and finally, there is one more. Now, in this all those cases we involve stress. Okay. There we involve stress, and those stress is tensile mode. Now, there is one more which is little different, but still it is a basically hydrogen related failure. We call it hydrogen blister. Okay. So, this is there, it is not involving stress, rather I would say external stress. Okay. So, here of course, this material must be having a stress component, external stress component. Okay. But here you do not have external stress component. So, that time, so if this blister also leads to failure or maybe delamination or kind of internal crack. So, that internal crack would be due to the internal pressure created by hydrogen gas. Now, why it happens, that we will talk in a little while. Now, coming to decohesion based, not decohesion, it is a dissolution based model. So, if we talk about dissolution based model, now there the first is pre-existing active path. Now, many metals and alloys, if this is the metal microstructures, if these are the grains, there could be either solute segregation along the grain boundary, one is solute segregation, just hold on. For A is solid segregation, there could be precipitation. Okay. So, now these two things can make a grain boundary either anodic with respect to matrix, or those solute, and anodic to, that means those solute segregation leads to a local region which is thin anode region compared to the matrix part. This precipitate could act as a soluble precipitate. Okay. So, this is one, and other option would be this precipitate itself is cathode, okay, and then that leads to a local adjacent anode region. In both the cases, you could see that the grain boundary area, this grain boundary area is vulnerable for dissolution. Okay. Now, let us say there is a crack. So, that crack is growing like this. So, this is the crack within this material. Okay. So, let me just put it in this fashion. So, here the crack is growing. Okay. So, this is the crack, this crack is growing, and this crack could be quite sharp now. Okay. So, this crack is growing. Now, here we have tensile property, tensile stress. So, this tensile stress tries to open up the crack, and this particular effects depending on the situation of that particular alloy system. For example, if it is a 304 SS stainless steel, where if it is sensitized, then chromium carbide would happen along the grain boundary, and then surrounding region will be anode. So, the thin strip will have intergranular corrosion. So, that intergranular corrosion will progress. At the same time, tensile stress will keep on opening the crack. So, that way the crack grows within the body. So, it's basically you have a crack. So, this is the crack, and now let us say this is the grain boundary, this is the grain boundary. So, this is the grain boundary, so this is the crack. So, the progress of the crack tip happen like this, and this is under stress. So, this tensile stress opens up. So, tensile stress opens up crack. So, this allows electrolyte or corrosive solution to reach to crack tip, and this will actually enhance continuous corrosion along grain boundary. Fine. So, that means so the crack opens, solution goes in, little bit of dissolution happens along the grain boundary, and then because of the dissolution, the crack can have a possibility to grow into that grain boundary portions, and then solution again ingresses in, and then continuous dissolution happens. So, the dissolution all the time is helping the crack to grow. So, this is pre-existing active path. So, that means in the beginning of the crack growth, we already have a situation in this particular alloy system that some portion of the particular alloy is vulnerable to dissolution. Here it is a grain boundary solutes or grain boundary precipitates. Now, this can clearly explain intergranular failure of sensitized stainless steel. In case of aluminum alloys also this can explain. For example, if you recall 8090 system, where we could see that copper rich precipitates are forming along the grain boundary, and that is actually leading to intergranular failure, and I have shown you how intergranular failure or fracture surface looks like. So, depending that can explain. So, in case of stainless steel, that to sensitized one, aluminum alloys. So, there this particular mechanism can clearly explain the SCC fracture. Okay. So, SCC, this mechanism can clearly explain it, SCC. Now, question is, in spite of the fact though it majorly could explain SCC in many alloy systems, but this mechanism only tells that if that particular fracture surface would be intergranular in nature, but it does not happen so. Sometimes transgranularity also comes into picture. In order to address that, so the other mechanism comes into play, which is film rupture model. In the film rupture model, let us say a crack is there. In the beginning, let us say there is no crack, and you have a load like this. Now, this material is passivating in nature. Okay. So, that means in that particular corrosive it can passivate. So, once it passivates, that means there will be a thin layer of oxides or hydroxides. So, this is the layer where oxides or hydroxide can form. So, it passivates, and this particular passive layer could be brittle, and because of its inherent brittleness, a crack forms in that particular film. So, when the crack, for example, here the crack forms, and when crack forms, some part of this particular section might get chipped off. So, this portion chips off. So, you have exposed section. Okay. And this is under tensile stress. Now, since this material is passivating in nature, so then immediately the passive layer would form. So, this initial passive layer is there, and the next passive layer would form. Okay. And then again this crack can break it like this. So, then a small portion is chipped off. So, then second time you have a situation like this. This is schematically drawn. So, like that way the crack propagates. Now, question is whether during crack propagation the crack stops for a while because it passivates quickly, and then that passivating layer is broken due to the tensile stress action, or this particular portion where the material is chipped off, that will keep exposed to the material solution and the dissolution would take place, and before the passivation happens. So, that depends on the rate of crack propagation and the rate of passivation, repassivation rather. So, that particular factor would be decided if this is greater than this. Okay. So, that means rate of repassivation is more than the rate of crack propagation. So, definitely the way this schematic has been drawn, the mechanism would follow like this. The crack breaks the brittle surface layer, and then again that another surface layer forms, and accordingly the crack propagates. So, that means crack is trying to break the surface film and then dissolution takes over. But if this is greater than this, that the rate of crack propagation is more than the rate of repassivation, then definitely once this crack happens, so this portion is exposed to the corrosive, and that continuous dissolution happens before repassivation takes place. So, some dissolution would happen and then the passive layer would form, because the rate of passive layer formation is less than the rate of crack propagation. So, in this case like that, then second level of course, this particular film will again be broken, and sometime this particular bare metal surface will be exposed to the solution and dissolution would take place till the next passive layer forms. So, like that way it goes on if the rate of crack propagation is more than the rate of repassivation. So, this is the mechanism where the rate of crack propagation is more than the rate of repassivation, and so this is this one, okay, and this is for this particular thing. Okay. So, like that way, so immediately the passive layer does not form. So, this is film rupture model that actually explains some of the transgranular mode of fracture. So, now in these cases it is not specific to the grain boundary, it can happen at any location. So, intergranular failure, if it is not happening due to pre-existing active path, then if it is not happening that way, then this could be the mechanism that could be followed. Okay. So, this is film rupture model, where the system which does not show any intergranular failure, there you can experience this kind of failure. Now, interesting part is you could see that why this is coming under dissolution mode, because this film formation is basically action of dissolution. At the same time, the growth is also action of dissolution, only the crack is only trying to break the film, that is it. The crack is actually opening the particular crack point and then allow the solution to enter into the crack tip. So, that is why the crack is basically the second fiddle, but you are actually dissolution is the main action here in case of film rupture as well as in case of active path process, pre-existing active path mechanism. Now, there is one more mechanism which is basically slip step mechanism. Slip step dissolution model. So, let us say we have a crack, this is the crack let us say, and this is the tensile stress that is active. Now, that crack tip, because there is a tensile stress and there is a triaxiality here and there are slip planes here. So, let us say these are the slip planes. These are the slip planes, and now because of that deformation of the crack tip, there could be a small deformation here. So, then it can be like this if deformation happens. Okay. So, now you could see that the small part section of it, this section has pushed into the material. So, this is the material part, this is the material part, and small deformation has got a slip in that into that material. Now, here you have corrosive. So, till this, when this happens, actually this particular, and if it is a film forming, so now there is a film also. There is a film also. This film is also existing. This is a passivating metal. So, now this film is there. Here also we have film. And you could see that this segment, this is a small portion which does not have film. Okay. So, that means this is the bare metal surface, which actually this part is dissolution takes place, fine, and then passive layer forms. Okay. So, then second step, it will further go like this. Fine. So, then this part is open now, and this is the passive part, and then this part again dissolve. And second time it can also take a different slip plane. So, instead of that it can deform this way. So, that time it will be okay. So, this part will be then, so this portion will be exposed now. So, like that way the deformation takes the material into the deformation actually allows the bare metal to get exposed, and then next step solution takes over and dissolution starts before the passive layer reforms. So, that means here also you could see that the stress here, the stress at least doing something more to this. It is not only opening up the crack, but at the same time it allows the deformation to happen along a slip plane at the crack tip, and then dissolution takes place. So, all the time the dissolution is coming into picture. That means the deformation of course is taking place. Here stress is actually not only opening up the crack, at the same time it is allowing deformation. In previous case the film structure model, it is only cracking the film, but here it also allows the deformation. So, that is what it is little different than this particular model, but here also you could see all the time dissolution rapidly takes the material away of that exposed slip step, and these are basically slip step. So, these steps are basically forming. So, this is a step, slip step. So, this slip step is exposed to the environment or corrosive, and dissolution happens, and before repassivation happens. So, that way the crack goes into the material. Okay. So, this is the slip step dissolution model. And the last one is corrosion tunnel model. In this case, you have a crack tip, let us say this is my crack tip. And the tensile stress is acting like this. Now, what happens? The corrosion allows a small tunnels to form, and those tunnels are actually, that corrosion tunnels is basically taking the material away along those small tunnels. Okay. So, this is the tunnels, and these small tunnels, they grow, tunnel forms, grows, forms ligaments. So, these are the ligaments. So, this small portion is the ligament, and those ligaments finally have ductile failure or mechanical failure, you can say. And in case of ductile material, there could be possibility of dimples. But question is, if that dimples happens on that broken ligaments where the dissolution did not happen, now the fractograph should show that. Fractograph is basically the image of fracture surface. Should show that, but it is not seen. Okay. So, that means there must be some issues with this particular model. Okay. Now, in order to address that particular issue, what happens? It was modified. The modification happens like this. So, initially it starts with small tunnel. So, this is going inside the material, those dissolved tunnels. Now, they take a form like this. Instead of maintaining that particular circular cross section, they become a slot pattern, and the slots are growing like this. And when this slot grows laterally also, so then what happens? This particular gap shortens. Okay. So, that means they become a thin section, very thin section, rather than this the kind of ligament what we have in the previous case. In this case we have ligaments, but here those ligament size dimension will be extremely small. So, that way so those ligaments will finally break, and then we have a fracture surface like this. So, like this a grouped pattern can be noticed. Okay. So, it would be a kind of interface, a fracture surface you can notice, and then it is a fantastic match between the two opposing fracture surface, and then we can address this problem of not seeing any dimples or mechanical failure marks of those small ligaments. What should be observed in this case, but it has not been observed. That is what this model has been modified. So, this is modified model, modified tunnel model. So, it becomes slot. Previously it was tunnel, and here it is second case it is slot pattern. So, that is the difference between these two, but here also you could see that the dissolution is actually initiating the SCC crack, and then finally the growth is also taken by the SCC crack. Growth of the SCC crack is also helped by this dissolution. Of course, the crack finally breaks open because of the mechanical failure, tensile stress that acts, but mostly it is a dissolution in the form of tunnels or slots that actually leads to SCC failure. Okay. So, this is the model what also falls under dissolution based model. So, now this is 4 major dissolution based model. So, now we will talk about cleavage based model in our next discussion or next lecture. Till then, thank you.